So this week we're going to look at the cascade transformer, and I'm just going to work through an example of the importance of certain things. So let's start backwards again. So we're going to look at a 200 kV generator, and we're going to look at a load of 100 picofarads. So I will be right. Our current on our high voltage will be given by 2 pi FCV. Right, so I get 6 milliamps, 6.3 milliamps. Our Q is going to be what? It's going to be 200 kV times 36 milliamps. So I'm getting a rating of 1,200. So let's work backwards and just look at a cascade type transformer. We're going to do a 2-stage. Right. So if you've got a 2-stage, we're going to have the voltage split between the 2 stages. So each stage would take 100 kV. Right, so we've got our input voltage Vm. Let's just say that the step-up ratio is 230 to 100 kV. What's this voltage here? It's also 230. It's the same as Vn. This is also a 230 to 100 kV transformer. Right, if we need to supply Q to the load, we're going to have to look at the ratings of each of the devices. So this top transformer here is supplying 100 kV and the current I. So your rating here is 600 VA. So the rating of the top part of the first transformer is also 600 VA. The rating of the bottom part is 600 VA. So the rating of your incoming supply is 1,200 VA. Right, so the difference between the cascade and the series resonance is exactly this. It's the incoming supply. Right. The one advantage is that as you go up by stages, your transformers get smaller and smaller. All right, so I'm going to swap back to my screen. Right, as it is explained here. So you've got your incoming, it steps up to V, note the connections here. And then you can see each of the transformers and the windings. The one issue with the cascade, and it's both a positive and a negative issue, is because you've got so many transformer windings, the internal impedance becomes quite high. So any harmonics or anything, they actually get transferred to the load. So you'll see it's not always a very nice waveform that you get out of the cascade. Conversely, it is a good thing because a lot of the time in high voltage we do breakdown testing. So because it's a high impedance, if you think about your transformer basics and your regulation, because there's a high impedance, the current causes a volt drop across the transformer and it prevents such a high fault current occurring. So that's the positive side of it. Right, we did the series resonant last time, but let's have a look at one last thing. One of the more modern techniques is to measure your high voltage at very low frequency. So we saw that the capacitance or the current drawn by the source is dependent on the value of the capacitance and the voltage. Capacitive reactance. So that frequency is a very important component. So at 50 Hertz, with a voltage of 12 kV and a capacitance of 15 nanofarads, our current would be 57 milliamps. Therefore, the power rating of our source would be 684 VA. If we reduce it to 0.1 Hertz, you can immediately see that our current is 0.113 milliamps and our rating is 1.36 VA. So with such a small rating, it becomes very portable to carry VLF tests around. It becomes very good to go to sites with VLF tests. You don't have to cart it around on a big truck. I'm not sure if anybody came across a series resonance where they put it on a big truck. Right, we're going to move on to impulse voltages. I've gone back to the system voltage table. Again, I'm referring to these in terms of testing. So any piece of equipment on a high voltage system, If it has a nominal voltage of 22 kV, for example, it needs to have a power frequency or a 50 hertz or an AC withstand voltage of 50 kV. Our lightning impulse withstand voltage would be 120/150, depends on where it's installed. So that's an impulse voltage. So it's not constantly alternating, it's not constantly applied. So the power frequency, it's alternating voltage, it's what we see every day on our systems. Lightning impulse, short duration, not constant, it's an impulse. Right. There's a few waveforms that we need to look at. We're going to look at the impulse voltage waveforms first. So let's draw our axes first, our V against time. And we're going to say that we've normalized the voltage to the peak of 1. Let's look at our red waveform. You can see it's got a rise time and it's got a fall time. Notice the shape in time of that impulse. We call this rise time the front time, and we call the tail time, sorry, the fall time the tail time. We have a definition of the lightning impulse waveform. The front time T1 must be 1.2 microseconds, and the tail time T2 must be 50 microseconds. So again, I refer back to that table. It's an impulse voltage. It doesn't occur all the time. It's not constantly applied. It occurs when there's a storm or there's a direct or indirect strike to a transmission or distribution line. You'll notice at the front of this waveform, there's a little curve. That's mostly due to testing. When you're testing with these voltages, you can't always get a front time that's perfectly straight. So we actually to find our parameters, to calculate these parameters in the lab, we define something as the virtual origin, and you can see it there in a dotted black line. And we define the time t between 30% to 90% of the waveform. And we've got an empirical relationship between t and t1. So t1 is equal to 1.67 t is equal to 1.2 microseconds. So basically that t1 is the time to peak of the waveform. So 1.2 microseconds. The time to 50% of that peak on the tail is defined as T2. So there you can see it, 0.5 or 50%. That's the tail time. We do have some other waveforms depending on the tests, particularly transformers. You chop the waveform by causing it to flash over elsewhere, and you see if your apparatus handles it. The target here is to get that oscillation, because that causes other issues in equipment. Just the last note, when testing, developing these waveforms or your impulse generators or your measurement systems, it's quite difficult to get something so accurate. So 1.2 by 50 microseconds, it's really, really fast. If you just think of charging a capacitor, you'll see that you don't always get an immediate voltage. There's a bit of a ramp up time. If you think about doing that over multiple capacitors at high voltage, it's not easy to get right. So they do provide tolerances. So T1 has a tolerance of 30%, plus minus 30%. So 30% of that time there. And similarly with the tail time, it's 20%. Our standard switching impulse, again, if we look at this table, you've got your switching impulse withstand voltage, and it tends to be at the higher voltages, the higher system voltages. In this case, we've got T1 or T peak. Because it's not such a fast waveform this time, the front time of 250 microseconds, we define it as where the voltage equals its 100%. Our tail time is 2,500 microseconds. And again, it's defined as 50% on the tail. So those are the two voltage waveforms that we look at. We're going to look at some current impulse waveforms. We're just going to define it here, and then we're going to look at it a little bit later. There'll be a video note that comes up. Right, so let's start with the axes. We've got a normalized current I and T. We've got the blue current there. Right, that looks similar to the voltage waveforms. That's what we refer to as a damped waveform. Again, we'll look at that in the video note as well. We again define a T1 and a T2. They have similar definitions of the peak and the tail time to 50%. We do have another type of waveform. So if you look at the red, it's kind of a damped oscillating waveform. So it's an underdamped waveform. If it's oscillating, it's periodic. So there are multiple peaks, multiple minimum and maximum. The definitions, T1 and T2, refer to the first peak. So it's the peak time for T1 and the time to 50% for T2. This part here, it's called an undershoot. Right? So the undershoot also has a peak, and it's always less than the first peak. Subsequent peaks will also be less than the previous peak. Right, so let's look at the impulse generator itself. So we've got a capacitor C1. We've got a switch. We've got an R1, an R2, and C2. Our initial capacitor is charged to a voltage V, so it's holding charge. While that switch is open, there's no voltage here. The voltage here is naught. So V2, the voltage that we want to look at, is naught. As soon as that switches, it switches in the second part of the circuit. So all the charge that is stored here will now move into the rest of the circuit. Right, so the first thing is the charge will flow through R1 into C2. So that means that the voltage of that C2, it will increase. Once that's fully charged, or there's a balance, C2 will then discharge into R2. So as it discharges, the voltage goes down. There's an approximate circuit there that tells you what's going on. We've got a charging time and a discharging time. That makes sense to everybody, I hope? Right, so the first thing is that this circuit is quite difficult to analyze in the time domain. So what we're going to do is we're going to convert the circuit using the Laplace transform and convert it to the S domain. So our fully charged source, or C1, there will be a voltage source. We'll have our capacitance C1. We'll have our resistance R1, R2, and C2. We again want to find the voltage across Z2 in this case. So if we just take our voltage divider rule, so V2, our voltage across Z2, be equal to the voltage from the source, V2 divided by S, Z2 divided by Z1 plus Z2. Right. We have our definitions of Z1 and Z2, and we can put those into the equation. From the top equation, we can reduce it to an equation that looks like this. And this itself is quite difficult to work with. So we're going to make an engineering judgment and make an assumption, and we're going to reduce this equation. We're going to open our Laplace transform tables, and we're going to see if there's anything here that we would want our system to fit into. This one here, it might be the right one. So we've got 1 over S plus alpha times S plus beta. If we look back at our circuit, we've got an S squared. We've got some sort of relationship there. Maybe we can select alpha and beta accordingly and see if our circuit is completely off. Right, so we select alpha equal to 1 over R2 C1 and beta equal to 1 over R1 C2. And we can start working with something a little bit easier. When we convert back into the time domain, we can see those exponential functions. And this all kind of makes sense if you consider your definitions of your impulse over here. Right, so one thing that you want to work through is I want you to take that equation, and maybe I can give you some numbers and you can work through that and find out if it's equal to the equation where you substitute in or what the error is. There's a couple of other definitions that we need to look at. The first is efficiency. So that's defined as the peak across V2 divided by your DC voltage, your input voltage, V over here. So it'll always be less than 1. So when we consider peaks or maximums in maths or signal analysis, we know that at the peak of the waveform, there is no gradient. The gradient is equal to 0. It's not changing. So we can set a derivative or gradient equal to 0, and we can start trying to find our peak values or our times to peak. So if we set dv2 dt to 0, we can start trying to find our t. We should know the rest of the values. We can rearrange our values, and we can rearrange it such that we find a value for t peak. We can also find somewhat of an equation for the efficiency. That can be confirmed with a sketch or a value, or if you just determine your V peak. Right, we're going to start the current impulse generator, and then we're going to go through it a little bit more on Friday. I'll also have a video uploaded for you later today, I hope. Again, we've got different types of waveforms. We've got our aperiodic or overdamped waveform, our definitions I peak and T peak, and T our time to 50%. Again, we've got an undershoot. So the current impulse generators, they look slightly different. A current impulse generator, we want to push current through our device under test. So that could be a surge arrestor, it could be a cable, it could be something where we need to show that it can withstand a high current. So if we charge up a capacitor to a certain amount, we can basically just discharge that capacitor into the device. So basically, we switch something and we short circuit that capacitor. So the region of times in this impulse generators are 4 microseconds, 8 microseconds. So the problem with the impulse generators is that you can't get away from inductance. It inherently exists in any circuit. We can set a resistance, and we'll see how to set that a bit later. So we've got high currents in the kiloamps and very fast, so that L di dt becomes very influential on the shape of the currents. Again, we can convert our entire circuit to the S domain, and we can analyze the current in this case. We get to the end of our current definition. V over L is equal to 1 over S squared plus RLS plus 1 over LC. If we again go to our Laplace transform, we see this equation here. That's the one that matches our equation that we've defined. And unfortunately, there's two solutions here. One The top one has a sine component with an exponential component. The other has a sine h component with an exponential component. Right, so again, I'm just going to go back to these waveforms. You can see that there are two different types of waveforms. You've got an aperiodic and a periodic. All right, so our periodic waveform is our oscillating waveform with that sine component and the exponential component which damps it. You can see that in the image there. Our aperiodic, is our sine h component, and you can see that that sine h, if you convert it to an exponential form, it's just a collection of, it's just a multiplication of exponentials. So it's not oscillating. So that's why we get this aperiodic waveform. Right, I'm gonna stop it there today. There are some video notes